Then, Piyush, you can start streaming.
Are we live yet on YouTube?
Pratyush, you're getting cut off a bit. Hello.
Am I audible?
Ha. You're audible now.
One. Okay.
Pratyush, if you're having troubles, I can do that. That's fine with you.
Am I audible now?
You're audible.
Okay, so yeah. So hello everyone to another talk by SEDS Celestia. And today we have Professor Jesse with us, University of Sydney. He specializes in the study of formation and evolution of galaxies. And today, for the topic for this talk is what do galaxies and shadow puppets have in common?
All right, wonderful. Thank you, Pratyush. Let me start sharing my screen for the talk today. Okay, so it is fantastic to be here today. Unfortunately, of course, it's virtual. But nonetheless, I'm excited to present some of my work to you today, halfway across the world. And the title of my talk today is a little thing that I discovered whilst trying to explain some of what I do to my little nephews and nieces. And whenever you're trying to explain something to kids, you really have to think about the easiest way to explain something, but also something that connects to them. And as I was trying to sort of tell what I was doing, I figured out that using shadow puppets, so these little things that you can do with your hands that get projected onto a screen, is a really good way to explain what I'm doing. So that's going to be my main thing for today. So in particular, what do shadow puppets and galaxies have in common? But of course, the overall thing that I'm trying to do is to understand the formation and evolution of galaxies. So I hope to sort of share a lot of that in this talk today as well. So who am I? I am a postdoctoral researcher, which means that I do a little bit of teaching, a lot of student supervision, but a lot of research as well. So I did my PhD at Leiden Observatory in the Netherlands between 2010 and 2014. And then I moved back to Sydney, where I started a postdoctoral research and am now a fellow working for the University of Sydney. So I'm mostly an observational astronomer. So I try to use these really wonderful, amazing telescopes all around the world, sort of very large telescopes, the Keck telescopes, but also in particular this telescope here in Australia called the Anglo-Australian Telescope, to try and understand how galaxies form and evolve. But of course, like all of us, I'm trying to answer some of the really big questions, or at least try to touch upon these really big questions in an attempt to sort of grasp the extra knowledge that we need to understand the universe around us. And the big questions that I'm interested in all revolve around this beautiful band of light that you can see in a really nice dark spot somewhere in the world. And this is, of course, our own Milky Way. This photo was taken by a colleague of mine, Dilyar, and it was taken here at the Anglo-Australian Telescope. And the one thing that I do want to say is, because we're here on the land, which is originally from the Aboriginals, I do want to mention that whilst giving this talk, I want to give my respects to the elders past and present from the Gadigal people from the Eora Nation. And so it's really upon their land that I'm giving this talk. So that's why I want to give my respect to the traditional owners of this land. So in answering these big questions, I'm looking in particular at our own Milky Way galaxy and how that galaxy connects to other galaxies. So in particular, if you look at this beautiful galaxy here that we're part of, our Milky Way galaxy contains roughly 200 billion stars, is a typical galaxy, which is a disk galaxy. That's why we see it as a long thin band on the night sky. I'll explain that a little bit further later on. But the questions I'm trying to answer are, for example, is the galaxy that we live in, is it unique in any way? Or is our Milky Way just a standard galaxy formed in exactly the same way as all of the other galaxies in the universe that we see around us? The other question that we're trying to understand by studying all of these stars is, how did our own Milky Way form? We roughly know that the universe is about 14 billion years old. But when we look around our own solar neighborhood, we see that stars are typically only 5 billion years old. So there's a lot of time after the formation of the early universe until the creation of our solar system, which is part of the big Milky Way galaxy. And another galaxy that I'm particularly interested in is the Milky Way the final product of evolution? Meaning, will it still evolve further, or is this how it's going to be for the next 20 or maybe even 100 billion years? And so let's begin a little bit by this little final chapter. Is the Milky Way the final product of galaxy evolution? And then the answer is no, probably not. And the reason why we know this is because we've got a neighboring galaxy called the Andromeda Galaxy. And so let's focus on this picture here on the top left first. So if you're in a really nice dark area and you've got our Milky Way galaxy here, then there's that tiny little thing right here where my pointer is, which is the Andromeda Galaxy. And the Andromeda Galaxy nowadays is really far apart, but when we measure the exact velocity and the direction of the velocity coming, then we actually find that the Milky Way and the Andromeda Galaxy are on a collision course, meaning that in about 4 billion years, our own Milky Way galaxy is going to collide with this other galaxy. And so some of researchers in the US, in particular Roland van der Marel, did these amazing computer simulations to try and imagine what that might look like in 2 to 4 billion years. And so every little picture here is part of a computer simulation that shows you what happens, what everything looks like today. Then 2 billion years later, and all of a sudden you see that this Andromeda Galaxy is a lot closer. Then in about 3.75 billion years, it's going to be really close. And 0.1 billion years later, you start to see that these two galaxies, the Milky Way galaxy that we're part of and the Andromeda Galaxy, are starting to collide. In 3.9 billion years, you see this really what we call this cosmic firework, where all of the gas from both galaxies get mixed, and that causes a lot of new star formation. But then around 4 billion years to about 5 billion years, this whole collision starts to settle down, and you end up with something after 7 billion years that looks like a really boring galaxy with not much structure in it. And these type of galaxies are called red and dead. Red because they have very old stars, which tend to be very red, and dead because no new stars are being formed within this galaxy anymore. And so what I'm trying to do in my research is to look at all of these other galaxies around us to learn something about how our own Milky Way formed, but also what might happen in this collision that was going to happen with the Andromeda Galaxy. So by studying hundreds and even thousands of other galaxies, we're trying to sort of bring this whole picture together, what might happen to our own galaxy. So in today's talk, I'm going to talk about some of the results that we came across a few years ago, 2 years ago exactly. And this had to do with the age of a galaxy, so how long it's been in its current shape and how old the typical stars are in it, in relation to the shape of a galaxy. So I already sort of said that there's roughly two types of galaxies. Some galaxies are really thin, that we call disk galaxies, and others are more roundish or spheroidal, and we call those ellipticals. And it turns out that there's a relation between how thick a galaxy is, or thick or how round, and how old the stars are in it. So let's have a look what that variety of galaxies in the local universe looks like. This was work that was discovered probably before we even knew that galaxies were not part of our own galaxy, meaning that when people first discovered these little islands, these little nebulae in the sky, they didn't know whether it was part of our own galaxy or if they were really extragalactic other island universes out there. So this is work from the Edwin Hubble, who is a really famous astronomer who has several beautiful laws named after him, but also the space telescope called the Hubble Space Telescope is named after him. And so Edwin Hubble was a perfect example of an extragalactic observer. So he spent a lot of time looking through telescopes and making these photographs on these photographic plates of galaxies, and then trying to understand how galaxies might evolve. And what Edwin Hubble found out was that if you look at the diversity of galaxies, so looking at all these little galaxies, he roughly put these into what we call a tuning fork. So you've got the main stem, and then you've got two forks going up and one going down. And here on the left, what he found was that you mostly have these roundish or smooth-looking elliptical galaxies, elliptical and lenticulars, he called them. Then up here towards the top right, you've got these galaxies that have increasing amount of these spiral arms. And down here, you've got galaxies that have spiral arms as well, but also have this really distinct bar shape, this bar feature in the middle. And so when you see something like this, you could think, well, given that we have this diversity from going from really smooth to really structured, maybe galaxies evolve from the left to right. Or alternatively, you can say, well, if things start out with a lot of structure, maybe over time they lose this and things actually evolve from right towards the left. And so the way to figure out which way this evolution goes is actually to look at galaxies that do not fall into any of these classes. So which are the galaxies that we call irregular galaxies, and what do they tell us? One particular galaxy that looks really like two galaxies that might be colliding is the Antennae Nebulae or Antennae Galaxy. And here on the left is sort of what you see if you take a really large area on the sky and try to take a photo of it, then you see this sort of two little heart-shaped pattern here. But then when you look with the Hubble Space Telescope, so you zoom in on this little green area here, you get the picture on the right. And you really see that there's maybe a core here and a core there. So this is really what we call a violent merger of two galaxies. And so these are two galaxies that probably looked a lot like these spiral galaxies before, but through this merging process, all of the stars get redistributed, the gas is mixed as well, which causes a lot of new young and hot stars to form, as shown here in blue. So this is really a galaxy transformation happening. And as I showed before, in the same way what happens to the Andromeda Galaxy and the Milky Way Galaxy, these galaxies are in a process of transforming probably into something that looks a little bit like this. So this is again one of these red and dead galaxies, but now we see that besides this really smooth light distribution, which you expect after such a big collision, you also sort of see these remnants of dust which might indicate that this galaxy was formed through such a merging process more recently. But the evidence that I've given you so far is a little speculative. I've given you galaxies that are sort of caught in the process of merging. I'm showing you sort of results that might exist afterwards. But the really best way to figure out what happens is if we were to look at this process in real time. The problem is, as I said before, this process probably takes a couple of billion years. So it's unlikely that we as humans will ever be able to observe such an event in real time. But what you can do is you can run computer simulations where you can speed up the entire process to see what goes on. And so in this little video that I'm showing here below, that's exactly what we did, is we took two galaxies and collide them. And I'm just going to go back one more time. So in the beginning, you see these two spiral galaxies colliding together. And in this process, you really see this dense elliptical structure forming, but with a lot of what we call tidal tails. But this computer simulation does seem to suggest that if I take two spiral galaxies, one that looks like this and one that looks like that, and I add these together, you get something that ends up looking like this really big elliptical galaxy. So if we go back then to this Hubble tuning fork, then we see something which is kind of interesting. So I've now sort of tried to convince you of the fact that these spiral galaxies, when they merge together, that they form something that looks like this. But it also means that these galaxies that here, these spiral galaxies, they tend to be disk galaxies. So they tend to be really what we call thin if you were to observe them from the edge on. Whereas if I look towards these elliptical galaxies here on the left, these are really round no matter how I observe them. So there seems to be that the shape of a galaxy, so its intrinsic shape, so no matter how I look at it, I define the intrinsic shape as how thick that spheroid is. That seems to be related to the formation history, where these thin galaxies are really young or in the early stages of evolution, whereas these round elliptical big fat galaxies tend to be old and probably in the last stage of galaxy evolution. And so in that work that we published 2 years ago, we actually found that this is the case. So just like humans, if you grow a little older, you start to get that little extra weight around that middle. And this is in humans what we call middle age spread, but galaxies seem to suffer from exactly the same thing. So in that paper, we had just a figure like this, where we show the age on the vertical axis, where young is on the bottom left and old is on the top, and versus shape, meaning that when a galaxy is really young, it seems to be thin, and as it grows older and older and older, it becomes rounder and more puffed up. Okay, so that is the theory, that's what we discovered. But how do we actually discover this? Because if we look at the night sky, it looks something like this. We're not seeing the three-dimensional structures of galaxies. Instead, we're seeing a projection of all of these shapes onto a 2D flat plane that we call the night sky. So if we look at a lot of galaxies together, we see some that are really round, some that are maybe really a little bit edge on, but that doesn't mean that this galaxy per se is round, although it's very likely that this one is going to be flat. But what I'm trying to show here is that projection is really important. So imagine that you're an alien and you're trying to study humans from space. Now, if you look from space onto Earth and you look at humans, this is probably something that you would see. And if you look at humans from the top, it's really hard to tell if they're young, if they're old, or if they're sort of middle-aged. Simply because from the top, it's very hard to see that this person here might be somewhat smaller than this person there. It's hard to tell whether someone is male or female, and it's even harder to tell how many limbs we have, because some seem to have 2, some seem to have 1, and others, well, some don't seem to have any limbs. So projection makes everything a lot harder. Of course, if you look down on Earth, you see that humans come in all shapes and all sizes. But here, for example, it's probably a little bit harder to tell whether humans are square, if they're completely flat, or if they're kind of roundish. So projection is really, really important. But how do you take projection into account when you look at something in the night sky? So imagine looking at these two galaxies. At first, you'd say, well, they both look really round, so these two galaxies must be very similar. But then you go to a different point in space, and you actually learn that the galaxy here on the left looks round, no matter what angle or inclination I look at, whereas this galaxy here changes as a function of inclination. And inclination here is nothing else than having that this galaxy look like this, where it's face on, where the inclination angle is 0. And as I make the inclination go towards 90 degrees, I actually observe something that is really thin. So as I said before, these are these elliptical galaxies, and these are these disk galaxies. So how do you figure out when you observe structures that look round on the sky that they're actually different in intrinsic shape? So the key here is that you need one extra dimension of information. So just by looking on the sky, you won't be able to tell whether something is round or whether something is flat. And this is where the shadow puppets come in. And you might be a little bit puzzled to think about, okay, we've talked about projections. What do shadow puppets have in common with this? Now, the trick here is, and I was explaining this to my nephews and nieces, we're sitting at a campfire and we're having a wall nearby, and I'm doing all of these funny shapes, like a little moose, I'm doing a little dog. You can do all of these amazing little things. And at first, my nephews and nieces, they're really amazed. They're like, wow, how is he creating all of these little animals onto the wall? And then they look at you and they're like, oh, he's using his fingers. And they realize that that two-dimensional projection that they see on the wall, that little animal in black and white, is actually made by having all of these little fingers. So they soon figure out that the fingers, that little extra dimension that you have, is the key to unraveling how these 2D structures were made. And this is true for galaxies as well. If you want to figure out whether something is round or whether something is really flat, you need extra information. And it turns out that that extra information is rotation. When we look at galaxies like these ones here, these disk galaxies, all of the stars are rotating in this little plane. It's like race cars going around this track. Whereas if you look at this elliptical galaxy here, that round thing, the stars within that galaxy don't all rotate in the same direction. Instead, they're going more like a swarm of bees going in all crazy, chaotic directions. So if we want to figure out how galaxies are built up, whether they're round or whether they're disky, we need to measure one extra thing, and that is galaxy rotation. Okay, so how do we do that? So this is a technique that we call spectroscopy. And I've got a little video to explain how we do this with the telescope that we have. So this is from the AAO, which is the Anglo-Australian Observatories that build the Anglo-Australian telescope that we use for our work. So this video is about 1 or 2 minutes. I'll just talk you through it. So the idea, this is called rainbow fingerprints. So it's all about spectroscopy. So we're getting light from a distant galaxy that looks something like this, travels towards our telescope. The telescope is about 8 hours north of Sydney, and it's called the Anglo-Australian Telescope. It has a giant mirror of about 4 meters in diameter. So this is 4 meters. All of that light travels here from the main mirror, which is down here, into what we call an instrument. In this case, it can either be the SEMI instrument that we use or another. But the key here is that all of that light that gets reflected is transferred into these fiber optical cables. So these little glass fibers where the light is focused into, and that is brought down by the telescope here all the way through the side to a different room where there is a spectrograph. So it goes through these optical fiber feeds and then into what we call a spectrograph. And the spectrograph, what it does is it transmits when it receives white light. So it's first going to hit a few mirrors to make sure that all of the different fibers that it gets goes into a prism. And a prism is the one that makes starlight, the white light, into a rainbow spectrum. So it separates white light into blue, green, yellow, and red. And so when it's gone through all of these complicated optics, lastly, then it's projected here onto this two-dimensional chip, which is simply our camera. And this is a camera that you also have, for example, in your phone. This is just a slightly bigger and slightly more expensive version of it. But when you see this, and I'm just going to stop it here for a second, every little line that you see here is light that comes through one of these fibers. So the telescope isn't looking at just one object, it's looking at hundreds of objects simultaneously, or for SAMI, what I'll show later on, it's actually a lot of fibers stacked together. But what you're seeing here is a spectrum of a galaxy, and a spectrum is nothing else than the amount of flux or the amount of light per wavelength area. So here you see it on the blue, and it goes all the way into the red. So spectrum tells you something about not only what kind of stars are in there, but it's also going to tell us how quickly those stars are moving. Okay, so how do we then measure velocity from the spectra? And this is the Doppler effect that you might have had in some of your physics classes, where if you have, for example, an ambulance or a car drive really fast by you, you get the change in sound, like doo-doo-doo-doo-doo-doo-doo. And so it's that change in tone that is caused by first the sound wave coming towards you, but then the sound wave moving away from you. And it's that differential in velocity that is changing the pitch of the ambulance or car. So this happens to light as well. When something moves really rapidly away from you, that light, as we call it, gets redshifted. That means if you take a galaxy spectrum that is shown here in the bottom. So again, you've got all of these little, what we call absorption lines, which are caused by certain elements. For example, here we've got the sodium line, but there's also lines caused by hydrogen, which are the Balmer lines, and Paschen lines further to the infrared. The point is that if you take this spectrum and you put it in an object which is moving really rapidly away from you, these typical lines get shifted towards the red end of the spectrum. If something's coming towards you, you would get these two lines that move towards the blue part, which is why we call that a blue shift, and it's a red shift if things are moving away from you. So the cool thing is, while this is somewhat theoretical, maybe, this is actually what we observe in galaxies. So we see that galaxies that are moving away from us are actually redshifted. And even within galaxies, we see that stars that are coming to, so if you take a galaxy that looks like it's rotating, one part will be moving away from you, whereas the other part will appear like it's moving towards you. So it's going in circles, and one part will be redshifted, one part will be blue shifted. So in reality, when you look at a galaxy spectrum, you see something that looks like this. So you've got blue wavelengths here on the left and red wavelengths here on the right. You've got all of these little wiggles here, which are caused by different elements or different molecules. And so what we do is, after we take all of these absorption line spectra, we measure how that light is redshifted or how it's blue shifted. And so, for example, here in black is what the observed spectrum is, and then in red, overlaid on top, which is very hard to see because it's a really good fit, is the actual fit that tells us the velocity of a galaxy. Now, as I said before, if you take a single fiber, so if you just look at a single galaxy, then you only get to know whether a galaxy is overall moving away from you or if it's coming towards you. But if I put a lot of these little glass fibers stacked together into this one bundle, then I get information about the velocity of the stars here in every single glass fiber around this thing. And this is what we do with an instrument called SAMI. The cool thing is that when you take all of these bundles, for example, within this white dashed line on this galaxy here, then what you actually see, and this is the velocity field of that galaxy here on the right, is that in red, we're showing stars that are moving away from us, and in blue, we're showing stars that are moving towards us. So for this galaxy, that looks a little bit like a disk galaxy, edge on, we're seeing that the stars are going away from us in red and blue towards us. So this is indicative of rotation along the axes that is shown here in this blue dashed line. And here's another galaxy, which is more clearly one of those disk galaxies. And indeed, when you look with the spectra on all of these positions, you see that again, blue means coming towards us and red going away. So this galaxy is actually rotating in the opposite way. And this is what we do with an instrument called the SAMI spectrograph. And what we did is you have here this instrument here, which is on the top end of the telescope. This is an old photographic unit, meaning this was used in the 70s to take big photographic plates of galaxies, and we revamped this, we rebuilt this to be an integral field spectrograph. So if you were to look here inside, you would see something that looks like this. So this whole part here was built in the 70s, but this part here in the middle is the new technology. So what you see here is all of these little cable bundles are these, what we call bundles of glass fiber. So for example, one of these metal things that you can maybe see here is something that looks like this, that is plugged onto this metal plate with a magnet on exactly the position where we know a galaxy will be. And then one of these little hexabundles is built up out of all of these glass fibers. So with this instrument, we can do 13 galaxies simultaneously per observation. So for every new observation, for every new galaxy field that we do, we completely change these field plates. So we have a plate that we drill new holes in, and then we plug one of these fibers in there to observe that galaxy. So this is done with the Anglo-Australian telescope. Of course, you know, it wouldn't be Australia if there's not kangaroos out there at the middle of night, which is when kangaroos go from being really cute and fuzzy to being really dark if you shine your torch on them. But it's in an absolutely amazing place in the Warrumbungles National Park. So this is the instrument. So I've observed a lot of nights with this instrument, but the other thing that we get in Australia is big spiders. And there's this one night where I'm observing, and together with my colleagues and my team, around 3 or 4 o'clock at night, we had to change going from one galaxy field to the next. Now, all of this is pretty much done in the dark. There's only one little light in that little top end. So as I'm trying to work away, all of a sudden, my colleague goes completely blank-faced, almost quiet. And I ask, what's wrong? And instead of saying anything, they just point towards something above my head. Now, at this point, I should probably explain that if you look at all of these fibers, because it's such a new instrument, every one of those hexabundles is worth about $15,000. So this entire instrument that I'm just looking here in front of me is worth about $150,000. The other thing is that these are made out of teeny tiny glass fibers. So if I twist or bend that little hexabundle a little bit too much, I would literally snap it in two. So as I'm holding one of these hexabundles ready to plug, a colleague says, right there above you is a spider the size of your hand. And it's sitting right here in this image. And all I could think at that point is, please do not jump on my head. Because if I were to drop one of these hexabundles or put my hand through it, I would ruin the entire semi-galaxy survey for the rest of its lifetime. So I told my colleague, whatever you do, just let me know if it moves. And I just started plugging away. And 50 minutes later, the spider hadn't moved. I was a little nervous, but we finished that plate. We moved out of the telescope and went observing. The next day, the spider was still there. We caught it and we threw it out. But then, of course, 2 days later, whilst observing in the operating room, we see another giant spider jump behind from the screens, giving us another fright. So I always joke that in Australia, you don't need coffee whilst observing. The wildlife will keep you straight awake. But going back to a little bit of the science, if you have a look at a plate like this, what it will look like for the telescope is that it's as if it's looking at all of these individual galaxies. So each one here is a galaxy, where a probe means one of those bundles. And so when you take all of the spectra and do all of your data reduction, what you'll end up with is something that looks like this. So you see these rotation of all of these beautiful galaxies. Some look really complex, others look a little bit more boring. But this is what we do with the Semi-Galaxy Survey. So it's integral field spectroscopy of about 3,000 galaxies. So what does it look like? Well, after the survey was finished, you get something that looks a little bit like this. So you get the rotation measurement of all of these galaxies, 3,000 in total. Galaxies of different sizes, galaxies of different masses, galaxies that look like ellipticals, galaxies that look like disk galaxies, galaxies that are in the process of merging. But the key part is that we have that little extra information now, that third dimension that we needed to tell something about what shape these galaxies are. So we can measure the shape from what they look like in the sky, but combined with how they rotate, we could tell whether they are actually intrinsically round or are intrinsically thin. So that's how we measure the shape of a galaxy, by not just looking at the sky and seeing what it looks like, by adding that third dimension that is called the rotational velocity. Okay, so that is one part of the puzzle. So I've explained how we measure the shape, but how do we actually measure the age of a galaxy? Okay, so let's do another analogy here. And the analogy is, imagine doing dendrology, which is apparently the study of wooded plants, but again, you're an alien and you have to do this from space. And you see an image that looks something like this. And you see it's green, so you probably think, okay, there's a lot of plants there. But if you had to estimate how many trees are there in that forest, whether that forest would be young or it would be one of those really old forests from medieval times, whether, for example, it would be consisting of oak trees or pine trees, and then if you also had to guess how many young trees there are versus old trees, it's a pretty big challenge. But this is exactly what we are facing with galaxies. What we see is just one projection of all of these stars, all of these different types, into one giant galaxy. And instead of looking at individual trees or individual stars within these galaxies, we're just getting millions and millions within one single pixel in our instrument. So how can we then tell the age of a galaxy? One crucial detail in stellar evolution is needed to explain how we measure the ages in galaxies. So by doing so, I'm going to explain this quite busy diagram, but I'm going to take you through it, so just bear with me. So this diagram shows what we call the luminosity, or the brightness of stars, where the brightest stars are here on the top and the faintest stars are here on the bottom. Then horizontally, I'm showing the temperature of a star, and that is related to its color, meaning that if something is really blue, it means it's extremely bright, or it means extremely hot. If something becomes redder, then you get a decrease in temperature, so you get lower temperatures here on the right. When something's red, the highest temperature here on the left. Now, if you look at our sun, which is sort of around here, then this gets luminosity of 1. This is simply a scaling we do in astronomy, where we typically tend to refer to things in units of our own sun. So if something is very massive, we tend to say, well, it's 1,000 times more massive or 1,000,000 times more massive than our own sun. But we do the same with luminosity. So our sun is what we think about a yellow star, has a temperature, surface temperature of around 5,600 kelvins, around here. And it's sitting on this, what we call main sequence. And the main sequence of stars is where they spend most of their lifetime. So stars are giant balls of hydrogen plasma, and after they have their initial fusion in the center go off, they spend a long time on that sequence, depending how massive they are. So it turns out that if you are a sun-type star, you will spend about 8 to 10 billion years on this main sequence. Now, if you're lower mass, you will spend a lot longer on there. So low mass galaxies can be 50 to probably 100 billion years, much beyond the age of the universe at the moment. So we actually haven't seen these extremely old stars yet. But what we do know is that these very massive stars that are really bright and really blue, meaning they're really hot, only tend to live for about 10 million years to maybe 100 million years. So these stars, very soon after they're born, relatively speaking, will explode, go off as supernovae, whereas stars down here live for a very long time. The key thing to take away from this is that if you see something that is primarily red, it means that you're probably old. If you see something that is really blue, filled with these young stars, you probably think that it's going to be very young. So color indicates age. Now, color indicates mass as well, because when you look at these very blue stars, you tend to see that they're very massive, whereas these young stars here are very low mass. Okay, so let's take that analogy a little bit back to that trees then. For example, if you look at a forest in the same way that different stars have different colors, you can actually tell that different trees with different leaves also have different colors. Oak trees tend to be a little bit dark green. These pine trees can almost look like blue, whereas these birch trees here are very light green. So the color of the leaf tells you something about what type of trees are in there. Then you can also sort of assume that an oak tree takes much longer to grow to a certain height than a pine tree, but an oak, which is really thick, tends to be heavier than a pine tree. So by looking at simply the color in here, you can already tell something about the type of trees that are in there and probably how old or how massive those trees are within that forest. The question is it really that simple? Well, probably not. This is a little bit of a stretch, of course. And one thing that I haven't taken into account is something that I'll demonstrate here by skipping through a few slides. So let's start with this. What I'm going to do is I'm going to run through a few sequences to see if you can figure out what might be changing here. So this is the first change. This is another change. And this is another change. And another change. And another change. So we're seeing the color of this forest change, in this case, as a function of time. So what I'm showing here is actually the 4 seasons, where here we have spring, the summer, here we go into autumn, here we go into winter, here we go into spring, and here we go into summer again. So the problem is that as a function of age, or as a function of time, this forest changes color. So in autumn, it looks something like this. In the spring, it might look like something like this. The other problem that I'm not taking into account is that the forest probably has a lot of trees that have already died. So if I were to ask how much mass or how many trees are in there, I should probably put in a factor to account that some trees might have already died. So the same thing is true for galaxies. We need to take into account the fact that stars evolve. So after a star has burned through all of its hydrogen, it transforms in what we call these supergiants, or into these giants that start fusing, instead of hydrogen in the center, start fusing hydrogen in its outskirts, and at some point helium and even carbon and heavy elements. But the key point is that you can take away, roughly speaking, if you look at a galaxy and you see that it's very blue, it has a lot of young stars. If it's very old, it will have a lot of red stars. So when you look at a galaxy like this, which is our Andromeda Galaxy, you can indeed say, well, if you look towards the center, you see a lot of these red stars, so it must be fairly old. But then when you look at this disk, you see a lot of these blue stars, and therefore it must be somewhat young. Now, this galaxy is really nearby, but if you look at galaxies that might be a little bit further away, that look more like these little blobs, these are the 5 galaxies I studied for my PhD that are probably in the very early universe. It's much harder to estimate how old these stars are within these galaxies. Now, the good thing is, when I explained how we measure the velocity of stars through the technique of spectroscopy, it turns out that that little trick works for age as well. Because when you look at a spectrum of a young galaxy versus a spectrum of an old galaxy, they look distinctly different. So here again, I'm showing the flux, so the amount of light as a function of wavelength, where blue is here on the left and red wavelengths are here on the right. Now, if you've got a young galaxy, it has a lot of blue young stars. So I see that this intensity peaks here very early on in the blue, and then all of that light fades away when you go to red wavelengths. But when you have an old galaxy, you've got much more light in the infrared and then very little in the blue. So the spectroscopy of a galaxy tells you something about its age. So in the same way that we measured all of the rotation for all of these galaxies within the semi-galaxy survey, simultaneously, we could also use those same spectra to reveal its age. And when you combine those two, you come back to this diagram here, which shows you the age as a function of shape. So just like humans, galaxies suffer from a middle age spread. These very thin galaxies, these galaxies that look like disk galaxies, are very young. And as we start to see those shapes transform from something thin into thicker and thicker and thicker, we start to see that the galaxy becomes older as well. So, in conclusion, galaxies, just like humans, suffer from this middle age spread. So in this talk today, I've gone through a lot of material. And just to give you a short summary, I've explained to you roughly about these 2 types of galaxies. So we have these spiral galaxies where we see a blue disk where lots of young stars are forming, whereas towards the center that looks a little bit redder, we have a lot of older stars. Then there's also this other type of galaxy, which is an elliptical galaxy, also called sometimes early type galaxies, which tend to be very massive because they form through these mergers, and they're filled with these old stars. So they're called red and dead. The other thing which I've explained, like for example, for our own Milky Way galaxy together with Andromeda, galaxies primarily evolve through merging. Throughout their life, a galaxy will collide with other galaxies, and through that process will grow bigger and bigger, but also rounder and rounder. And then for our own Milky Way, unfortunately, it's going to be a rather big, violent mixing process that's going to happen in about 4 to 5 billion years when we're going to collide with the Milky Way galaxy. And that final process will transform our beautiful spiral galaxy into something that we call a boring red and dead galaxy. But whether something is really boring depends on the observer, because personally, I find these massive ellipticals that are the final stages of galaxy evolution remarkably interesting, because they give you all of the clues of how the galaxy might have looked like a couple of billion years ago. And so with that, I'll conclude my talk and I open it up for questions.
Okay, that was a really, really interesting talk, sir. So I have a few questions. First of all, my major question has to involve with the merging of different galaxies itself. Like you showed that when these different galaxies merge, they form a mostly elliptical, or like their bulge can increase, and so what happens to like the angular momentum of the 2 galaxies? Like, does it get I don't know, distributed in a sense, or does it still have one major axis of angular momentum, or
that's a really good question. So what happens to the angular momentum of these 2 spiral galaxies when they collide? So the trick here, as we normally say, the devil is in the details. So if two galaxies are both spinning, say, clockwise, then when they tend to collide, they tend to conserve a lot of that angular momentum. So instead of something that has a lot of chaotic orbits, what you tend to end up with is something that will look a little bit spheroidal, but most of the stars will conserve their angular momentum and they actually go in the same direction. Now, if you have two disks where one is spinning counter rotation towards the other, then the overall angular momentum of that entire system, instead of going from angular momentum into orbits that go in one direction, the stars go into these chaotic orbits. So what we normally tend to say is instead of things go from angular momentum into what we call pressure support. So if you think of star particles a little bit like gas particles, like a hot gas, then you can imagine that if you have got a cool gas where perhaps everything is in the same, going in the same direction, if you heat up that gas, the particles start to bounce around more and more. And so when we talk about galaxy dynamics, we tend to say that these circular orbits are cold, but when you start to get stars, galaxies, for example, colliding, which have counter-rotating orbits, you start to get something that looks like a really hot pressure-supported spheroid. So the angular momentum gets transferred into this, what we call dynamical heating. So instead of having the angular momentum, they go on to these more random orbits.
Okay, that kind of makes sense. I'll have to read up a bit more on it. And during that collision, like, do you have any idea what happens to the dark matter content of the galaxy?
Very good question. So what happens to the dark matter when galaxies collide? So we know that galaxies are surrounded by these massive halos of dark matter. Now, the one thing we do know is that dark matter is a non-collisional particle. And the reason why we say that is because if there were to be a collision between these particles, it has to exchange energy in some way, and that's something that we would observe as light, which doesn't make it dark matter anymore. So dark matter halos tend to merge together as well, but without colliding. So the dark matter halos will be the first to overlap and to touch. But what happens typically is that the stars within those dark matter halos, they don't feel anything that is outside of their shell. They just feel the stuff that is going towards it. So in the end, what you get is just a bigger halo with more dark matter, but it doesn't have any clear features that we tend to observe. So most of the visible effects of galaxy mergers are all in the star particles and in the gas particles. Did that answer your question?
Okay, so I was kind of relating it to the bullet cluster, right? So
Yes.
There's a lot of gravitational lensing happening over there, and we think that's because of the dark matter, because we can't really observe all of the major gravitating zone. So
Yes.
yeah, I was kind of getting to that analogy.
Yeah. So okay. with the bullet cluster, which is of course two merging clusters, I think it's slightly more complicated because the halos are probably bigger. But the details, so I have to imagine that for galaxies, you probably get similar complex structures, maybe very shortly. But I have to admit that I have to look up the details to see what would really happen to the dark matter particles, to see if you would get any of these lensing signatures within galaxies. I don't think we've ever observed that, but that could be a scale thing. Whereas, the bullet cluster is really massive on the sky and was found mostly through a lot of hot gas where you see this, and then through gravitational lensing, we found out about the dark matter and its complicated patterns.
Yeah, that means there's a question in the messages. If the universe is expanding at an accelerated rate, how will the Milky Way collide?
Yeah, that's a very, very good observation. So we know the universe is always expanding. And so you can imagine that if something is always expanding, why would anything ever collide if you have that framework expand? the question always is, how strong is the gravitational pull of something that is nearby you versus how fast the universe is expanding? And this is what we call sort of local gravitational wells, where in the system between our Milky Way and Andromeda, even though the universe is slightly expanding, the gravitational pull of these two galaxies is strong enough that they can resist that underlying framework of expansion and still be attracted to each other. So, for example, when galaxies are in pairs or slightly further apart, like the Milky Way and Andromeda, they don't feel that underlying expansion of the universe anymore. As compared to all the galaxies that are really far away, where they don't feel their gravitation, it looks like everything is moving away from each other. But as soon as you're in each other's gravitational spell, in that bound, that underlying expansion of the universe becomes irrelevant for your local area, so to say.
So there's another question in chat. What would happen if these combined galaxies combine with other galaxies? Can the shape of the resulting galaxy also be predicted?
Yeah, so that's also a great question. So what happens to when we have consecutive mergers? The more you merge, the less clear it becomes what the initial merger product was. And so what I mean by that is that you can have one of these really what we call major mergers, where two galaxies are sort of equal mass. If they merge together and everything gets reformed, then it's very hard to find out what happened before that major merger. So, for example, we know our own Milky Way galaxy is being bombarded by other smaller galaxies all the time. And so two really beautiful examples of that are the Small and Large Magellanic Clouds, which are satellite galaxies already on an interaction orbit with our own Milky Way. Another galaxy which we know is colliding currently with our Milky Way is called the Sagittarius Dwarf Galaxy. And that first collision happened probably about 3 or 4 billion years ago. So we know that you have a process that is called minor merging, where you have smaller satellites colliding with galaxies. And we tend to see those effects a really long time ago. So if we're in our Milky Way, we can probably trace back everything that collided up to about 8 or 9 billion years. But about 9 billion years ago for our own Milky Way, at the time, it had what we call a major merger. So something that 9 billion years ago was about as massive as our Milky Way that collided together. But probably because the orbits were aligned, so the stars were going the same way, it didn't become an early elliptical, but it remained its angular momentum and stayed in that disk shape. So after we collide with Andromeda and you build this very big elliptical, it's going to matter a little bit whether the stars of the Milky Way and Andromeda are going to be orientating in the same way, or if they're going to be counter-rotating. Nonetheless, say as you've got one of those really big galaxies, if it comes across another really big galaxy, it would probably just become more massive, but the shape might not change too much. If you bombard it with a lot of small galaxy, again, the overall shape might not change in the outskirts. But the interesting thing is that when you have something that penetrates towards the center, it can actually reform a little disk in the inside of a big elliptical. And so we actually do see signatures of these. If you look at a galaxy like, for example, the one down here, so these very massive ellipticals, very often what we see is that they have what we call a kinematically decoupled core, meaning they're stars that are rotating in a very different way as compared to all of the stars on these outer orbits. So if you look detailed enough within these galaxies and measure what, for example, the age and the dynamics is within every little spot in the galaxy, you might be able to trace back that merger history for a long time. Therefore, if I see something coming in and colliding with our own galaxy, I can probably also predict what the outcome is in terms of its shape. I hope that answered your question.
Okay, so there was also another question. like we used color to tell the velocities relative to us and the age in the spectrography, right? Um, so in that we measure like the distance between the different spectral lines, and then we can predict how much it has shifted, right?
Mm-hmm.
So is there any situation in which these two, the distance also increases or decreases, or uh, like these two parts move at different rates, or is it improbable?
So can you repeat the final question again?
Okay, so like in measurement of
Mm-hmm.
the like in the spectrography of galaxies, in of the light coming from the galaxies, uh, we measure the distance between two spectral lines to
Yes.
gauge whether these lines have red shifted or blue shifted, because we can't really compare them directly.
Mm-hmm.
So what if these two lines also, the distance between these two lines increases or decreases because of some phenomenon, or is it improbable?
Um, so I think I understand the question. So, but if I don't, please just rephrase it after I give my answer. So there's a lot of things that can impact where these lines are within the spectrum. And so, of course, the overall one, if the entire galaxy is rapidly moving away from us, all of these lines will be shifted as compared to what we call a rest frame, or a galaxy which wouldn't be moving. So whenever we measure things within a galaxy, we're always measuring it relative to its overall redshift or blue shift, meaning if I combine all of the spectra together, I get one single redshift. But so what we then measure within galaxies is just a little variation from that, what we call that systemic velocity. So a little bit redshift and a little bit blue shift, which is causing the back and forth movement of those lines. But I'm not sure if I answered that question completely.
I think that makes sense. Uh, I'll tell you if the person who asked it
Okay.
questions.
Happy to follow up.
Yes.
I think.
Oh, okay. I had another question from a viewer. He asked, like humans, do galaxies shrink thin, or do they always increase? Or have we not observed such a large time? Like these combined galaxies, can they eventually shrink down on
Yeah.
a really large time scales?
Okay, that's interesting. I've never thought about it in this way, but yes, galaxies can both gain mass and galaxies can lose mass, depending on where in the merging process you happen. But not only so, there's multiple layers to this question. Not only galaxy interactions can cause stars to be gained or lost. There's also other processes. So let me first begin with that merging. So imagine you have two galaxies which are not just going to be merging, but they're going to do what we call a flyby. So the orbits are not going to be exactly close enough that this galaxy is going to collide. But imagine that we've got one very massive galaxy and a smaller galaxy, where the smaller galaxy will do a flyby, will feel the gravitational pull, so it gets ripped apart a little bit, and then part of it will go away and the other part will remain with that other galaxy. Now, from the perspective of the galaxy that did the flyby, all of a sudden, because it encountered something that was a lot bigger and a lot heavier than itself, all of a sudden it would have lost maybe half of its mass. So galaxy interactions, when it's not actually a merger, will cause a galaxy sometimes to be stripped of its stars and its gas. The other thing is, in that video, I think that I showed, let's see if I can just quickly pull it up, because it will probably explain it kind of nicely. Just give me 1 second. I think I have it here. Okay. So what you can see here as well, when it merges, you actually see a lot of material being thrown out. When these two galaxies collide, probably if one was, a mass of 1 and the other one was a mass of 1, the final product would probably not be exactly 2. It would probably be maybe 1.6 or 1.7, simply because in that process, some of these stars will reach something that escapes the gravitational potential, and so those stars will be shot out and lost forever. Now, there's also another process which can actually eject a lot of material from the galaxy. And this is a process that we call galaxy feedback. And so I talked briefly about the end of a lifetime. A star, if it's massive enough, can go supernova. And that explosion is so powerful that everything that is in its vicinity will be blown out. Now, this is mostly going to be gas that is being ejected. But again, if that supernova is powerful enough and the galaxy is small enough, you will actually have a lot of that gas being ejected out of the galaxy, meaning the galaxy will lose its total mass a little bit every time one of those stars explodes. For more massive galaxies, where we know there's these extremely massive black holes in the center, you get a similar process, which is what we call active galactic nuclei, where material that falls onto the black hole creates an accretion disk that gets extremely hot and causes these two massive jets to cause, again, a lot of energetic particles being spit out of the center of the galaxy, taking all of the gas and heating it up and throwing it into the halo. So this also removes a lot of the hot gas, a lot of the gas that is in the center of galaxies and pushes it into its halo. So yes, galaxies do shrink, as well as that they gain mass, depending on what kind of process you have. Thank you for that question.
There's also another question in the chat by Sriram. Is there a reason for why the red type of stars are present at the center of the late type galaxies and the blue/younger stars are at the outer side? I find that structure very peculiar.
Yeah, thank you for that question. It's a very good observation that, when you look at this galaxy, for example, here in the top right, that most of these redder stars are in the center, whereas the blue stars are sort of in the outskirts. And so the main reason for this is that we think the center of the galaxy, the stars either were formed a lot earlier, meaning that bulge component, that central thickening, was formed a long time ago, whereas these young stars tend to collapse into a thin disk, so more in the outskirts. The other reason could be is that all of the stars in this galaxy say that everything was formed at the same time. If there is a process like I described before, where you've got something that causes all of the gas to be expelled from the center first and then later on towards the center, the stars in the center would no longer get all these young stars because that gas was removed by this feedback mechanism, whereas in that disk, you could still get a lot of stars because that gas is not as hot as yet. So there could be two reasons. Either it could be that center part was formed a long time ago, and then as that galaxy keeps rotating, only in that in the outer parts where you've got that disk, whereas in the center it's more chaotic orbits, you would have forming stars. Or in the center, there's a process which causes star formation to cease, causing the inner part to look redder because there's no longer young hot stars forming. So it has a lot to do with either the formation history or how star formation stopped within that galaxy. But it's an ongoing study about how galaxies, as we call, how they quench and how that bulge formed. So yeah, structure points towards a lot of different processes.
So I have to add that I read in a paper that especially in spiral galaxies, because of all of the different arms, there's a lot of pressure on the gas present in those arms. And so those rotating arms of the galaxy are a hotspot for birth of newer stars.
Yes.
So could that also be the reason?
Yes. So again, it comes back to a lot about how stars actually rotate within these galaxies. And the beautiful thing is the spiral arms, for example, the one, I've got one, of course, on my Zoom background as well, which is a beautiful spiral galaxy. The spiral arms itself, the reason why we see these little spiral arms is primarily because that's a region where there was a lot of young hot stars being formed at that point because of pressure waves that go through these galaxies. So it's not that it's an actual physical arm which rotates on the sky. What you have instead is, you can imagine it being something like a pancake where some ripple is forming through, and everywhere where you've got one of those ripple going up, you've got a lot of gas being pressured together, and that pressure causes young stars to form. So every time where there's a ripple going up, you get these blue young stars that are visible. But the shape of the pancake itself, meaning how thick it is and how dense it is, doesn't change too much. So spiral arms are really only an effect of young stars being formed there, rather than being actual overdensity in terms of the number of total stars or in total mass.
Okay. Yeah, like it's quite interesting to, study these. There are so many dynamics involved in studying galaxies, It's just so interesting.
It's amazing.
I don't
I had a question.
have any more questions. Oh, yeah, sure.
Yeah, so when you're calculating the relative velocities of the rotating galaxies, you will also sort of have an idea of how far it's moving as a whole, right? So,
yes, correct.
Like in the galaxy survey that you were talking about, are there any applications of studying the expansion of the universe, or the dark matter interactions of Hubble constant or something?
Very good question. So so we do measure, of course, what we call the redshifts of all of these galaxies. And in order to measure the expansion of the universe, you actually need two different measurements of its velocity or of its distance. So what we typically tend to do is we say redshift, so that movement of those absorption lines towards one end goes into a velocity, and then we use something that is called the Hubble expansion law to actually calculate its distance. Now, if you want to calibrate that law, so if you want to study how fast the universe is expanding and whether there's accelerated expansion or whether it's just a constant, you actually need to measure both that redshift and an independent measure of the distance simultaneously. And so the way that's mostly being done is by looking at supernova. And the reason why people use supernova to measure distance is a little bit in the same way that if you have a lighthouse, and it's a standard built lighthouse with a certain amount of light bulb in it that shines a certain amount of wattage, then by measuring the amount of light that's coming from that lighthouse, how far away it is. Like if it's really faint and you measure only a percentage of that light, you know that it's going to be a lot further away than the lighthouse, which is really bright and probably standing next to you. Now, the key thing is that you need to know that every lighthouse is built exactly the same way as its other one. Otherwise, you might not know how to calibrate it. And the beautiful thing with supernova, in particular supernova, what we call type 1a, which is probably caused by a white dwarf. So it's a star at the end of its life, getting enough material that it goes into supernova mode. That process is really well controlled. So every supernova that looks like a supernova we call type 1a, we know exactly how bright it should be. So if you observe one of these supernova in a very distant galaxy, you can measure its total amount of light, and then you can calibrate that amount and measure its distance. So what you need to do in order to test this Hubble law, this Hubble expansion law, is measure not only really accurate redshifts from the spectra, but you also need to find a supernova that is going off within one of these galaxies. So this is, of course, why there was a Nobel Prize awarded to one of the scientists who's actually in Australia at the moment, Brian Schmidt, who's at the ANU. But he was awarded a Nobel Prize for measuring this expansion and figuring out that the universe is actually expanding accelerated. So then coming back to your question, are we doing this for the SAMI Galaxy Survey? And the answer is no, simply because we haven't seen any supernova go off within our galaxies in our survey. So in order to measure this Hubble law, you actually need to target galaxies where you see a supernova to go off. And so this is a big numbers game where you just keep observing the same patches of sky over and over again in order to find these supernova to calibrate. But this is not something that we did within the SAMI Galaxy Survey.
Oh, right. That's very interesting. Thank you.
Right. Thanks.
Does anyone else have any more questions? Oh yeah, Abu has one in the chat. When we use multiple fibers for studying a galaxy, can we also determine the angular velocities? What kind of information do we get from this?
Yeah, so that's a very good question. So, of course, we measured what we call the line of sight velocity distribution. So in the same way that when we see the distribution of all the light projected on 2D, we're also seeing that, of course, for the velocities. So we can only measure a velocity, what we call along a line of sight. That means that when we're looking at a galaxy, for example, the one here, say that you put 61 fibers on this galaxy, then every little fiber will probably contain hundreds of millions of stars within it. So you're getting the angular momentum, angular velocities of all of these stars combined, but only pointing towards you. Now, the beauty is that, of course, that if all of the stars within that galaxy were going at exactly the same speed, exactly going the same way, you'd still get a distribution in velocities, because stars at the back are probably rotating slightly different as stars in the front. So what we're seeing is you get sort of a Gaussian, where the middle is exactly that velocity that we're after, but you're also getting a spread in that distribution. So that spread that you're seeing is what we call the velocity dispersion. And the velocity dispersion is telling you something about how fast the stars within that line of sight are moving as compared to each other. So the cool thing is when you do that measurement, that velocity dispersion, that spread, and you do it in a disk, you actually find a lot of the stars are going on the same type of orbit in the same direction. Whereas, so in that case, that distribution will be really small because all of the velocities are the same. Whereas if I were to look within these elliptical galaxies, stars going in all these random orbits, so along a line of sight, I actually get probably very little velocity information, but a lot of information from the velocity dispersion. You can go even further. You can say, well, what if that distribution is not Gaussian, but it actually is perhaps a little bit skewed or even sort of flattened and boxy on the top? All of that gives you information about the stellar orbits. And when you get this line of sight velocity information, you can actually try and reproduce this by building a galaxy model. So you can say, what if I take a gravitational potential and I just throw a single star in it? How will that star look on the night sky? What if I add 2? What if I add 100? What if I add 1,000, 1,000,000, 1,000,000,000? Then all of a sudden you can use this orbital information with that gravitational potential to try and reproduce what you see here in the night sky. And once you combine all of that information, you can come up with a really good model of how each individual star within that galaxy rotates. And this is a method called the Schwarzschild stellar orbital method, developed by Schwarzschild, I think in 1979. But it's one of the most powerful techniques that we have to try and figure out what all the orbits and the angular momentum of all of these stars within the galaxies are.
So in all of the galaxy survey that you showed us, I saw that there was nothing like it wasn't. There was always like some part of the galaxy moving away from it. But if you saw a galaxy head on, so that a spiral galaxy, you see it from the top. Well, I haven't done the calculations, but what would the Doppler shift effect look like for the orthogonal movement from the upper side and the lower side clockwise?
That's a really good question. So let me see if okay, so I don't know if you can fully see the top row of this image here, but this image here of all of these galaxies from the semi-galaxy survey were actually sorted by how fast rotation is from one side to the other. So here on the bottom right of the image, you see that there's really strong, like dark red and dark blue, and that's indicative of rapid rotation. But as you go up in this diagram, you start to see that that color, that little blue and little red, gets fainter and fainter. Whereas in this top left regime here, you're seeing galaxies that maybe look more yellow than actually being red or blue. And so what you're seeing here is exactly what you're pointing towards, is that when you're seeing galaxies mostly face on, you would hardly see any rotation, because if a galaxy that is edge on, you see the stars, of course, going maximum towards you and maximum away from you. But if it's face on and all the stars move perpendicular to your plane, you wouldn't see much velocity profile at all. And so that's what you see here partially. So some of these galaxies are indeed these face-on spiral disks. The other ones, some of these in here, are actually big ellipticals where there is no overall rotation anymore. So trying to figure out whether something is a face-on spiral or a big elliptical without rotation requires a really detailed imaging analysis. But yes, inclination is a really important factor that we need to take into account when we're measuring these, when we're trying to measure the absolute rotation of these galaxies. That's a very nice observation. Thank you.
Oh, so for the discussion about face-on versus no rotation at all, could you have like a sort of different distribution based on the Doppler shift effect that happens to the orthogonal movement? I mean, that's basically what I was asking. Like, would we be able to differentiate a galaxy which is just moving away from us through expansion, or versus a galaxy which is moving face on? Will there be a difference in distribution of the velocity in the upper side?
Not because of the expansion, because the rotation within the galaxy itself is mostly confined to its own gravitational potential. So within a galaxy, stars don't feel that expansion anymore. So the overall redshift due to the expansion of the universe will be the same for a galaxy face on or edge on. So you wouldn't be able to detect that kind of difference, unfortunately.
Oh, right. I meant exactly. So you were talking about we can differentiate a face on versus no movement at all. So I was trying to how do you do that based on what math can you use?
Yes. Okay. So whilst you don't see the individual rotation from one part to the other, the overall galaxy would still be redshifted. So that redshift effect is visible no matter whether a galaxy is face on or edge on. It's just within the galaxy itself that you won't be able to detect the rotation of the stars. But the overall, we call systemic velocity, doesn't change due to a galaxy being face on or edge on. So you can almost think of it as the Doppler shift in the lines is caused by two things. One is the expansion of the universe, which causes an overall shift towards a certain what we call redshift, and then within that little on that redshift, you get a little bit of red and a little bit of blue. But overall, the expansion of the universe is the biggest dominant effect of that redshift, whereas the back and forth, it is tiny. So for comparison, the redshift is probably in thousands of kilometers a second away from us, whereas the rotation from one side in the galaxy to another is only plus or minus 200 kilometers a second usually.
Right. Thanks.
All right. Thank you. So I see a question in the chat from Abu. So the question is, how do you think your research depends on simulations? I believe a large part of the semi-data would go towards validating or correcting simulations models we have. Yeah, that is a very, very nice question. And it really goes beyond of what we do and we're trying to do here is of coming up with observational evidence for how galaxies merge and evolve. But of course, if you run a large computer simulation, you want to have certain parameters that you can check to see if your simulations, for example, even reproducing the basic quantity of galaxies. So the way cosmological simulations work nowadays is that you begin literally at what we call probably a couple 100,000 years after the Big Bang. We use the imprint of the universe at that point, which is called the cosmic microwave background. And we use that to start a simulation. And at the beginning, it is mostly dark matter particles that clump together that form these little overdensities. But these simulations incorporate the hydrodynamics of the gas and the dynamics of all the particles in there. So they literally evolve these simulations for 14 billion years and then try to see at the present day universe, after all of that evolution, whether it looks the same. So in order to check whether your simulation actually reproduces the universe, you need to measure certain things like the mass of the galaxies compared to its size, how big the rotation of these galaxies is, what kind of orbits the stars are on, how old the stars are distributed through the galaxy. So these are all parameters that the semi-galaxy survey can provide to these simulations to make sure that they're actually predicting the present-day universe correctly. So there's a strong interplay between using these simulations to understand the physics that's going on, but also to use a semi-observational survey to test that the simulations are actually making the right predictions. So yeah, it's a very good question. Thank you.
Thank you so much for answering all of these questions. I really hope it didn't take too much of your time.
No worries at all. Happy to answer any questions.
Does anyone have any more questions?
I'm sorry. Can I ask you another question?
Of course. Go ahead.
This is really interesting. Okay, so basically, it feels like intuitively there should be a correlation between how fast the galaxy is moving with the age of the galaxy. And is there something that you guys have found in the survey or in any other kind of research?
So in the sense of how fast it's moving away from us, or how fast the galaxy is internally rotating?
Yeah. It's about rotation.
Yeah, so there definitely is. So in the way that you can think of galaxy rotation as being one of those thin disk. And so if you see very rapid rotation, that seems to be indicative of young age. The problem is that there's also a relation between how massive a galaxy is, so how many stars are in there, and how rapid it is rotating. And this is, you can calculate this with Newtonian dynamics, but if you've got a really small galaxy with a lot less mass, then the maximum rotation that you expect in these low mass galaxies is a lot smaller as compared to these very massive galaxies where the rotation is a lot faster. So whenever you use, whenever you want to say, okay, this galaxy is rapidly rotating, you need to correct for the fact how massive it is. Now, the other problem that we have is that you can actually have a galaxy which is really thin, which is rotating rapidly, and something that is maybe not perfectly round, but perhaps a little bit thicker. So say that, you know, one is extremely thin, the other one is 20% thicker. Both galaxies can still have the same maximum rotation, but one is a little bit thicker than the other. And so just rotation, unfortunately, is not enough to get a really accurate measurement on its age or its shape. But if you take into account that velocity dispersion, so how different the stars look, how much variation there is within their velocities, you get a lot closer. So if you use the combination of both measuring the rotational speed and the spread in their dispersion, you come a lot closer to estimating a galaxy's age. And that you can do actually pretty independent from how massive a galaxy is.
Oh, right. And what about the percentage of like, if we can find out how old the stars are, and like percentage of how many older stars are in the galaxy, is there any way that we can like correlate it to the distance between us, in the sense that younger stars will probably be farther away because light is gonna reach later on?
Yeah, so that's a good point as well. So we definitely know that early on in the universe, probably roughly between 2 and 4 billion years after the Big Bang, the largest amount of stars were being formed. So when you look back in time, you definitely see a period in cosmic time when almost all galaxies were forming stars. Now, the problem with that is that you can't, some galaxies, as long as they have enough gas in their vicinity, will keep on forming stars all throughout their lifetime. So the key here is a galaxy, in order to make it look old, you need to stop that star formation in one way or another. So one way I told you before is by having a process that either heats up the gas or removes it from the galaxy altogether. But there's other ways as well. So galaxy interactions, for example, tend to strip away gas from a galaxy. If a galaxy, one individual galaxy, comes across a really big group of galaxies, it also removes a lot of its gas. So star formation itself, so the amount of young stars, does not necessarily correlate with how far away it is. So there's a lot of different factors that come in that determine whether a galaxy is star forming or whether it's quiescent. And distance is only marginally important for that.
Okay, thanks a lot.
No worries. You're welcome.
Okay. All right then. I guess that's it for this lecture. Thank you so much, sir, for taking out the time and teaching us about all of this wonderful stuff. And it was a really, really insightful and fun lecture, and we really enjoyed having you here. And thank you everyone for attending this. We hope to see you soon in our next one as well. Thank you so much, everyone.
You're most welcome. And thank you to everyone for attending today and for changing the time for my lecture to make it not midnight for me. So I really appreciate it. And it was a lot of fun talking to you and answering your questions today. Hope you're all well, and all of you, please stay safe.
Thank you so much, sir. Thank you so much. It was a really wonderful lecture.
Bye-bye.
Bye, sir. All the best.
All the best to you too.